Section 1.8, Linear Transformation. To begin with, let's see what transformation is. Transformation is a function or a mapping or a rule of correspondence which assigns every vector in one vector space to one vector in a different space. The simplest example of transformation is good old function, which we have seen this in previous classes. What is a function? Function is a transformation which assigns each value of x in the domain to one and only one value of y in the range. So there is a transformation, meaning under this rule, which means what? The transformation of x is equal to y. That means for every value of y, which we select in what? In the domain, the image of that particular value of x is y in the range. So the diagram shows we have a transformation from real numbers into different set of real numbers. So this guy is called rule of transformation, t of x equals y, and we read this as mapping of x into y under the transformation t. Notice the transformation is mapping from what? A set of real numbers to a set of real numbers, as the domain and the range of the real value functions happens to be a bunch of real numbers. Suppose now the function is x squared. So using the transformation notation, you write t goes from one vector space, which is what, R, to a different vector space, which is a set of real numbers. And let's say the rule of transformation is defined as t of x is equal to x squared. So every time you pick a value of x here, the image of x, or the transformation of x, becomes x squared. So t of x equals x squared is also known as the rule of the transformation. So we come from domain to the range, and these are real numbers, so are these guys. For example, if f of 2 is equal to 4, so that means the transformation maps 2 into 4. Okay, notice we use the word into, not onto, into 4. Under the transformation, what? T of x is equal to x squared, and then again, transformation is from real numbers to real numbers. So 4 is called the image of 2 under the transformation t. And 2 is called the pre-image of 4 under the transformation t. In general, transformation is a rule of correspondence, also known as mapping, where it assigns every vector v in what? Vector space v to one and only one w in the vector space w. And this is how the transformation is shown. The transformation is from v into w. However, v is called domain and w is called codomain. We don't call this range. A bit later, we'll find out the range is a subspace of W. In other words, range is part of the codomain, so we don't call this range. It's called codomain. Range is just what? Subspace of codomain. Okay, the rule here is, transformation of V is equal to W, and the mapping is defined, in general, from V into what? W, from V into W. So W is not called range because range is a subspace unless, the transformation is onto, where W matches the range, so W becomes the range. And we are not going to go over that topic. Some examples of transformation. The transformation here is from what? Taking the square matrices and transform it to, again, square matrices. But the rule of the transformation is what? Anytime you take a n by n transformation, the image of it, after it goes under the transformation T, is the A transpose. So which means transformation of T maps any n by n matrix of real numbers into other n by n matrix of real numbers using this rule. Okay, so what happens here? We go from mn to mn, and the rule is T of A is equal to AT. Anytime you choose a matrix in vector space V, the image of that matrix under this transformation is the A transpose. The other example will be going from the transformation is from from all polynomials of degree 1 or less into polynomials of degree 2 or less, which is defined by this. Notice the image of this first degree polynomial is the second degree polynomial. A and B are real numbers, which this means transformation is from polynomials of first degree or less into polynomials of degree 2 or less, and they are defined by this rule, and A, B are real numbers. Sometimes you may have like transformation from set of continuous functions over a closed interval A and B into set of real numbers, and the rule of transformation is the transformation of function f is definite integral of f of x dx, you know this function, between A and B. In other words, these are set of continuous functions, but the image of those continuous functions under this transformation is a bunch of real numbers, because the definite integral gives you a bunch of real numbers, right? So the transformation equals the integral of f of x from A to B with respect to x, and so this integral, definite integral, is called the image of f under the transformation T. F is called the pre-image of of this this integral under T, and that's basically some examples of transformation. Sometimes the transformation involves a matrix. In other words, the transformation of vector x is AX. A is an m by n matrix. When they say find the matrix X, where the image under the T is B, and the transformation is from Rn to Rm. Remember, the matrix is m by n, so the domain is same dimension as the columns of the matrix A, and the codomain is has the same dimension of rows of matrix A. Here is matrix A, here is B. So what does it mean to say find the vector x whose image under T is B? Well, that is exactly the same as what? What would be the solution of this system of equation, which happens to have the constant column vector as 6, -7, -9. In other words, this is your coefficient of matrix of coefficients of the variables. Here is your independent variables. So this is the column vectors of variables, and that's supposed to be equal to this. So when you form a system and you solve this, you get this. So what is it that we just found? We just found the image of this vector, -5, -3, 1, under this transformation is B, which is 6, -7, -9. In other words, we just found the solution to this system of linear equations. So this guy, the solution gets to be mapped to to that column vector. And remember, this W is a codomain, which is R3. So is the domain, which is R3. So the image of -5, -3, 1 under this transformation is 6, -7, -9, based on this rule right here. Incidentally, that matrix A is called matrix of transformation, correct? So now that we know a little bit about transformation, it's time to talk about linear transformation, a special kind of transformation. Once again, let V and W be vector spaces, a mapping from T to W under T, V to W under the transformation T is called a linear transformation from V to W or into W if it satisfies two conditions. Okay, if we pick what? Two vectors in V, not W, but in V, right, in the domain, and the transformation of the sum of the vectors happens to be the sum of the images of those vectors, and the transformation of scalar multiplication of a vector in V is C times the image of that vector. If these two conditions are satisfied, then we say the system is what? A linear transformation. The transformation is a linear transformation. This kind of reminds me of what? Conditions for subspace, remember? Addition and the scalar multiplication operation. It's kind of like that. Alternatively, sometimes people combine these two and just go linear. We have the transformation is linear if and only if the transformation of C1V1 plus C2V2 equals C1 transformation of V1 plus C2 transformation of V2 for all the V1 and V2 in the domain, and C1 and C2 in the, and they are real numbers. So let's take a look at a couple of examples. Suppose the transformation is from continuous first derivative continuous functions to continuous functions. So this is V, that's W. And the rule is the transformation of any function is the derivative of that function. Verify that T, the transformation, is linear. So what do? You take two functions in V, which happens to be all first derivative continuous functions, and C is a real number. So take the what? Transformation of the sum, which if you go right here and replace this guy with f plus g prime, and now manipulate this, you get f prime plus g prime, but that's exactly the transformation of f plus transformation of g. Why? Because by definition, transformation of f is f prime, transformation of g is g prime. Remember, f and g are in what? Domain V. On the other hand, the transformation of what? Scalar multiplication. You go back here and replace this f with cf, manipulate it, and you get this. But f prime is the transformation of f. So therefore, two conditions are satisfied. Therefore, the transformation is what? A linear transformation. Okay. So now, counterexamples. Not all the transformations are linear. Suppose the transformation here is from M2 to R. Instead of all 2 by 2 matrices of real values to what? All real numbers. And here is how it's defined. The transformation of those matrices, the image or the transformation of those matrices happens to be determinant. Is T a linear transformation? Well, let's see now. Once again, you select two matrices, namely A and B, in what? In V. Remember, this is your what? V. This is your what? W. And here is the transformation. You always, rain or shine, select your what? Objects in V, not W. Okay, because they happen to be in V, so they have to obey this rule, which is T of A has to be determinant of A, T of B has to determine of B. Now let's see what happens to the transformation of summation of those two matrices. Well, according to this, if I go here, replace this guy with A plus B, and here I replace this A with A plus B, unfortunately, determinant of A plus B is not the same as determinant of A plus determinant of B. In other words, this is not the same as TA plus TB. So the first requirement for being a linear transformation failed. So there is no need to what? Verify the second requirement. Therefore, the T in this particular case, the transformation is not a linear transformation. What would be the application of transformation, matrix transformation, that is, in real life? Well, they use it in computer graphics. If you have like, let's say a matrix, like let's say 2 by 4, you can what? Translate by, let's say adding what? 3's to x's and 2's to y's. That's called translation. You can do dilation. That means if you multiply the matrix by a scalar, 3, that makes this matrix wider. If you multiply it by 1/2, that makes it what? Contraction. Reflection, these matrices, 1, 0, 0, -1, reflects the matrix about the x-axis. This matrix reflects the matrix about the y-axis. This one reflects about the origin, and this guy reflects the matrix about the what? Y equals x-axis. We also have rotation. This particular matrix, what? Rotates 90 degrees, generates 90 degrees. This matrix generates 180 degrees. This matrix generates 270. For instance, let's say I have this, this would be the vertices of a triangle, like let's say V1, V2, V3. There goes 1, 2, okay, 3, 5, and -3, 4. Suppose I multiply this by this rotation of 180 degrees matrix, and lo and behold, I get this. Now this is like V1 prime, V2 prime, and V3 prime. So guess what? This guy 180 degrees rotates and becomes this. So therefore, what? We have 180 degrees rotation. Matrix transformation, besides being used in computer graphics, it's also in cryptography, which is writing or solving codes. All right. So these are some of the applications of what? Of transformation. And that's basically what we're going to do. Of course, we will do more examples later. Thank you.